Hi! I'd like to introduce you to a guest who's been here for a few weeks and will soon be leaving. This is the Bose 1800 and it's professional, solid state even. Doesn't get much better than that. It's basically just a stereo amplifier. This thing puts out 2 times 200 watts and 250 watts, an 8 ohm, 2 times 400 watts or something in 4 ohm. Nowadays you would get a Class D module. It would be about 10 by 10 centimeters, it would do the same thing. But you know, this is the 70s. This is real heavy hi-fi amplification. I'll show you what I've done here a little bit. So, one channel here, one channel there. It's extremely basic. You've got a giant transformer there, giant caps, which means giant voltages. The thing runs off plus and minus 84 volts. This is built to last. The only problem this amplifier had, according to the owner, is that when you switch it on you get a giant pop. And because of that I have built in, zoom in a little bit, a little relay module. And what the module does is it simply waits a few seconds and then connects the outputs. In this little 3D printed case is a power supply, and that just feeds that thing. There's one thing you have to be really careful about with these Chinese modules. You can find them on AliExpress, which is that the outputs, there are 4 contacts switched here. These are the pluses, left and right, and these ones, the minuses, are connected to the same ground that the circuit runs off of. So if you have a Class D module or any other module that has bridged output, that is not gonna work for you. Be careful there. Here it works fine because this amplifier, the outputs are actually ground referenced. Another very nice feature is this little relay here, and what that thing does is, this is a resistor that is put in series with the input to the transformer, and it's an inrush current limiter. The relay is switched on by the secondary voltage. So when this thing is switched on, the relay is not on and the power goes through this resistor and the inrush current is limited. When the secondary voltage on the caps goes high enough, that relay is switched off and then you have all the power directly from the transformer into the rectifier. Now one thing you have to be careful about is when you switch this thing off, that relay takes a few seconds to disengage. So when you switch this thing on, it takes a few seconds, then it gives you the full power. You don't switch it off. You have to wait until you hear that relay click and turn off again, because if you switch it back on before that relay has disengaged, your fuses go out and you'll be in the dark. Ask me how I know. Let's see how much this boy weighs. 26 kilograms. Now this scale is not calibrated because it thinks that I weigh 85, so it's obviously wrong. Now before we give this back to its owner, it needs to be tested, verified, and of course the new functionality, the relay, needs to be double checked as well. Also this panel here has a little bit of malfunction that I still want to investigate. We have the amplifier connected to big dummy loads. Gain is at 0. Here we go. Turns on. And the relay switches on. Switch it off. And wait for the little relay. There. Now you can turn it back on. I'll switch it on one more time, and this time you will see the output relay module getting power and then switching the outputs. That's the anti-plop. The second thing this relay does, it actually monitors the output voltage, and if that goes over a certain amount, then it will actually switch it off 50 millivolts on this side, 170 millivolts on this side. That's well within spec. Now before we do anything, let's just check that we get the right voltages. Everything is referenced to chassis, so that's quite easy. On. This one gives 0, 0. Minus 82 volts and plus 82 volts. We have power. Alright, here we go. This is the start screen for APX. You'll see that I have only 5 channels active. That's because I have connected the amplifier inputs, I think on channel 4 and 5. Yeah, that's what you can see here. We can, yeah, we're capturing the cursor, okay. Let's turn the amplifier on. Okay. And I like to give it 440 Hertz. And we'll give it a very modest 100 millivolt. Remember that I have the gains set to 0 right now. Turn the audible monitor on. Here I want to see the waveform. You can actually see the offset voltages here, very good. Now I've turned my signal generator on, and let's see if we get any output. Okay, so we know the amplifier works. So this is one of the tests we have to do, which is why it has this little check mark here. Another test that we're going to do is a frequency sweep. Now it works. So you'll notice here that this is all at 100 watts with a real load. So we'll see that the amplifier can get pretty hot as well. Okay, let's see. The gain is about 30 dB, which is what we want. The relative level is where I've actually added 2 limits, and the limits come from the data sheet. It specifies that at this power level it should be plus or minus 1 dB, and you see only around 20 kilohertz, a little bit. Let's see, minus 0.2 dB, which is these days critical for a Class D amplifier, but for a Class AB from the 70s, it's brilliant. Deviation between 0.1 dB again. Now we've also measured THD plus N, and it's a little bit over. Let's see what happens if we repeat the measurement. Yep, it happens again. So it's very mildly out of spec.
A few moments later.
Interesting. One channel is very distorted. So it looks like we've blown up something here, because you see half of the waveform is missing for channel 4. The other thing that happens, what you hear right now, is the DC offset module switches off the output, and that's because if you take the average of this signal, it will be somewhere over here, and that's too much DC. Here we have the service manual that you can find on the internet, and here is a troubleshooting guide. And what was the first thing we were looking at? We were looking at excessive distortion. And the causes here are defective Q7, Q8 and Q25. And then when you take a look at the schematic diagram, you will see that Q7, Q8 and Q25 are all in the same spot, and they are in this dotted area, which is indicated to be the current limiting circuitry. Now the current limiting is supposed to stop the signal, and the rest of the amplifier is supposed to make the signal. So it could well be that these three little transistors cause some distortion. Now, when we go to the part list, which today would be the bill of materials, we see that Q7, Q25 are a 2N3904. Q1, Q3 to 10. No, they're all 2N3904s. Now, going back to the circuit, I am sure you can substitute any bipolar transistor in there, but I'm going to use 2N3904s. So let's take these three transistors out and put them back. Here we have the left channel module removed from the amplifier. Just look at that. Even the transistors are marked Bose. Now I can't directly see any damage, but the transistors in the biasing circuit are the ones over here. Let's see if we can get some focus. And they look a little bit meh. Now normally I would measure this stuff, but because it's an intermittent issue and because I can only measure the performance of this module when I actually put it under power, and that means I have to run more heat through it and it's not attached to the heatsink right now, and also because these transistors are pennies, I'm just going to replace them. Upon closer inspection, I think these transistors have been replaced already. Which doesn't mean I'm not going to do it now, but look at this solder tin. It's fresh tin. Q7, Q8 and Q25. 1, 2, 3. Even this one has been replaced. I'm still going to do it, but it's interesting. Alright, the panel is back in the amplifier. I haven't replaced the thermal paste, so it's going to have to come back out. This is just a little test. I can't test this thing without this big ass heatsink. Let's give it a little bit of signal and see what comes out. Ah, look at that. So the question is, will the top of the waveform disappear on us again, eh? Oh, look at that! Look over here. Distortions are very similar now. That's good. We had channel 4 a lot higher than channel 5 before. This is looking good. We're already at 30 watts. Oh, this is very positive. He's a happy boy. Outputting 100 watts. Far, far below the distortion limit set by Bose. Coming up on 200 watts. Very good distortion. 240. 250 is the spec. It's already passed. And now we're starting to run into the power supply rails, clipping.
5 minutes later.
Ah, we have a problem again. Ah, the old problem is back. Bad news, we didn't fix it. The distortion has come down. So we did do something, but after warm-up we have still lost half of our output power. So here we have CR18 has been replaced. Right next to it is R18, red, orange, violet, red, 23.7 kilo ohms. And on this side we have CR19 and R20, and it's exactly the same situation. These two versus these two are the current detectors, and this one would switch off half the waveform, and this one would switch off half the waveform. So if these diodes had any problem, this could be what's happening. CR5 is over there. I've replaced that just because I wanted to replace CR18 and 19. I have enough diodes to actually replace all of them. I'm not sure if I want to, but these are definitely potentially part of the problem. So we replaced CR18, CR19 and CR5. Alright, first of all we're going to turn it on. No explosions. Relay engages. We are on. And we have a half signal. That's bad. So, no fix. So, a little update. I've decided to remove the module from the amplifier. Have it lying on some plastic, but still connected so that it can actually run and I can probe stuff. Now, clearly it is not connected to the main heatsink, so it won't run full power all the time, but you know, this little internal heatsink is not too bad. I have connected it back to the main ground. Heatsink is supposed to be grounded. That's where you have another channel to confirm this stuff. And now I can actually poke all the parts on the lower side of the PCB. The first thing we're going to look at is the output of U1, the op-amp. Just as a sanity check, I want to see if I have a full sine wave over there. If I haven't got anything over there, I can easily forget about the rest of the amplifier. Alright, we're on and we have a good signal. So the theory of a bad contact is coming back. Something gets temporarily short-circuited. Look at that. Going bad, going bad. And we're good. We have a bad contact somewhere. That's all there's to this thing. Doesn't that just sound like a bad contact to you? Of course, I ran out of battery right when I found the issue. So we'll do it on the second camera. Here is R1. The signal on R1 is okay. From R1 we go to R57, right over there, into U1. Now I'm going to try not to electrocute myself. I'm going to measure the signal at R57. And it's gone. We now have a clean signal. You see? Now the question is this because I'm attaching a probe? Or is it because I'm actually pushing on the resistor? So what we're going to use this. It's not my actual toothbrush, it's what I use to clean circuit boards. But it's plastic, non-conductive. I'm just going to push it again. And we are quiet. Look, I'm not touching U1. Could be the circuit board here. Could be the resistor. This is a prototypical bad contact. Alright, so what we have done is on the bottom of this PCB I have resoldered every joint, each and every one of them. And the idea is that if there is something loose, one of these joints is going to give you a pop and just resolder. Now, none of that happened. I just resoldered everything and then I cleaned the board. My desk is filthy, so a lot of schmutz came out of the board. And when we turn it on, it doesn't work. So I went back to measuring this, I went back to poking the board, nothing changed. And then I saw this. Let's see if we can focus. There, right in the middle. We have a broken diode. And this little bugger is called CR8. And what I think is that it was barely hanging on all this time. When you put the board vertical, it was actually pushing itself back down, and maybe the bottom was falling out. When you put it horizontal, there was less stress on it. But this thing clearly needs replaced. By the way, what is so interesting about our buddy CR8 here is that its legs were sort of stretched. It's hard to really get it in focus here. Whereas all the other diodes had this funny bending going on. Actually, this one I did myself, but these ones here are original. Focus. So these legs were bent back and forth to allow for thermal expansion. And the only one that doesn't have that, see, CR17 has it. The only one that doesn't is our good buddy CR8. There. And it got to him. So this thing was built for eternity, with the exception of CR8. Here we have our old CR8 and the new one. I ordered a bunch of 4007s because why would you order a 4001, of which I apparently have a 50 or so? Why would you order a 4003 if you can just get a 4007? They'll cost the same. So that's going in there. Just to give you a look of the bottom side of the PCB. This is where CR8 goes. But what I wanted to show you is how clean it looks and how all of the soldering points have been redone. Literally each and every one of them has been reflowed, and that's how we got to the error. Half of this board was full of crusty old flux residue. The 1N4007 is in there, and I have immediately mounted the channel back into the chassis because YOLO, this has to be it. Swear to God, if this is not the problem, this thing goes out the window, and because it's 40 kilos, it's not going to be nice for the people down there. Power is on, audio precision is connected, inputs are not connected. That really does help. Input left and right. Dummy loads are on. Let's go. We're on. And what does it look like? Yes, we have two good waveforms. That doesn't tell us anything yet, because we have to give it a few minutes. The question is whether we should replace or clean up those 6.3mm inputs, because they're a bit loose, you know, like any 44-year-old. Okay, we're going to run the whole sequence. Serial number 006034. Go! DC offset fits. Frequency response looking good, not switching off. And here's the famous distortion versus power. The one that killed us every time. And we're going to pass this time. I feel it. I know it. Distortion takes a little jump down here because we're moving out of the crossover dominated area. As the signal grows bigger and bigger, relative distortion gets smaller and smaller. So from that data and the schematic you can probably calculate where it was biased. Not that anybody would care. And we're doing great. Look at that. We have a full pass. Absolutely brilliant.
2 hours later.
We are playing heater rather than amplifier. We've been running 250, 240 watts for a few minutes already. Heatsink at 42 degrees on both channels, that's fine. But what's definitely heating up are these big dummy resistors. I mean, these are not small resistors. And they're now 95 degrees. Woo! Ow, ow! Definitely too hot to touch. These are enormous resistors and they are burning out. Coming up on 100. The other channel, same thing. A little cooler. Or am I just measuring it wrong? Yeah, 87, 90 degrees. And the amplifier, this, no problem to touch. This is cool. So that just goes to show you what kind of an amplifier this is. The load is burning. I have to be careful that the plastic wires don't melt. But this amp, meh, no, we're fine. Why am I doing this? I want to stress test this a lot. And my little DC relay box is cool as can be. That's very nice. Because we wouldn't want any overheating here to start melting the 3D printed case. That would be bad. So the power supply is totally cool. It's heating up a bit here, but no, that's emissivity, I think. Definitely some heat on the heat sinks. 50 degrees, come on. Again, the load. 110 degrees. Holy shnikey. And it really smells like the dust of those resistors is burning. It is incredible. And I can feel it getting warmer in the room. 110 degrees. Boonk. I just heard the resistors expanding. They made a noise. I am not joking. This is unlike anything any amplifier would ever have to do. Full power, full time. And this is why 70s high-end audio, or just 70s professional audio, is something that you will never see in the current days. No Class D amplifier module can do this. This is how you take the front panel off. It's 1, 2, 3, 4, 5, 6, 7, 8 screws. And this is the LED indicator panel. We have on the top 2 LEDs that don't turn on, right channel clipping, and somewhere on the bottom, I'll have to review the footage, a couple of LEDs not turning on. Alright, here it is. It's a little crusty, I'm gonna have to clean that up a little bit. And the good news is these transistors, I'm sure you won't be able to read that, they're 3904s, so That's the type I ordered a bunch of, because that's actually also running the bias circuit in the stage itself. So I'm gonna figure out which channels, which transistors control the upper clippers and some of these lower LEDs. Once I figure out which one it is, we have replaced a bunch of transistors. The second light here was permanently on, so I've replaced both Q103 and Q104. The fourth light on the left channel is permanently on, so I've replaced Q6. And the two clipping lights on the right channel were permanently off, so I've replaced Q110. Powering it on, we have no lights on. That's a good sign. And we are going to run the audio test. Ah, there we are. We have the first two lights. Second two. Very nice. Light number 3. Light number 4. Okay, all we have to see now is the clipping lights. Let's just double check the other lights. It's looking very good so far. Come on, boy. I'm sick of working on you. Okay, clipping lights. No clipping lights. Yeah. Of course we have to measure AC. We're now measuring on the other channel, CR15. When we put a full signal on, we get 0.6 on the gate. So now it's back to CR115 to see what the other channel does on AC. You can't see it, but this is AC. Let's see, what if I put this to 30 Hertz? Yeah, not sure you can see the flicker on the camera, but there is actual AC signal on the gate. Cool. So here's the problem. We are taking 400 millivolts and you actually see the LEDs a little bit on. 390, 380, it's falling down. Alright, I think I found something. This is the voltage on CR15. I've swapped out this resistor, nominally 15 kilo ohm, which is R120, with R20, nominally 15 kilo ohm, except this one was 13 kilo ohm and this one was 16 kilo ohm, which makes this a lower resistor divider to minus 85 volts. So this LED would come on later, really just too late. So I thought if I just swap these resistors, the problem will move to the other channel. But as we will see, the problem did not move to the other channel. It became balanced. Let's run the sweep. $15 millivolts. Here we go. The lower two come on. second ones, nicely together, nicely balanced. Last LED. This channel seems a little bit brighter than the other one, but there's nothing between it. And now the clipping. Look at that. Let's go back to the clipping. If I turn it on, we see 600 millivolts AC on that transistor. So yeah, that turns it on. Nothing wrong with that. Good stuff. And let's just finally test it with some audio.
This is my voice on the left. This is my voice on the left-hand side. This is my voice on the left. This is my voice on the right. This is my voice on the right-hand side. This is my voice on the right.
Nice clipping.
This is my voice in the center. This is my voice coming from both left and right. This is my voice in the center.
So, all is well that ends well. This little boy has been remounted. Rear panels are straight and undented. Performance is good. LED panel works. It's playing music that you can't hear because it's copyrighted. And it's time to say goodbye to my little guest. I call him the little one now, even though he's half my weight and can break my legs. I'm gonna miss you, little one, but I will come to visit you very often. See you later, people.